Good morning, students, and welcome to the lecture series on Fourier transformation. In the previous two lectures, we have studied about what is the Fourier transformation, Fourier cosine transformation, and Fourier sine transformation, and basic properties of these Fourier transforms, and solved some problems based on these basic properties and definitions of Fourier transformation, Fourier cosine transformation, and Fourier sine transformation. In the continuation of the previous two lectures, in this lecture, we shall study about what is the convolution of two functions, what is the Fourier transformation of the Dirac Delta function, what is the Fourier transformation of the unit step function or Heaviside function, and in the last, we shall study about applications of Fourier transformation to solve the initial value problems and boundary value problems. So let us start with convolution. In mathematics, convolution is a mathematical operation on two functions f and g that produce a third function expressing how the shape of one is modified by the other. Or in mathematical, the convolution which is represented by star f star g of two functions f of t and g of t is defined by convolution of f and g is equals to integration from minus infinity to plus infinity f of u g of t minus u du, or this convolution is symmetric in the two functions f and g. So this can also be written as integration from minus infinity to plus infinity f of t minus u g of u du, which is convolution of g and f. So this is the mathematical definition of the convolution of two functions f and g. And now next one is convolution theorem for the Fourier transformation. Suppose that f of t and g of t are piecewise continuous, bounded, and absolutely integrable over the real axis minus infinity to plus infinity. Then the Fourier transformation of the convolution of two functions f and g is equal to the product of their Fourier transformation times root of 2 pi. Right? So this is our convolution theorem. For the detailed proof, you may go through any book related to the Fourier transformation. And special remark here, by taking inverse Fourier transformation of this convolution. All right. So Fourier transformation of the convolution of two functions is equals to product of their Fourier transformation times square root of 2 pi. Now, if you take the inverse Fourier transformation of this relation by using the definition of the inverse Fourier transformation, we obtain that convolution of two functions is equals to integration from minus infinity to plus infinity f of omega g of omega times e raised power iota omega t d omega. So basically the inverse Fourier transformation of the product of two Fourier transformation is equals to the convolution of their respective functions. Let us see the application of this convolution theorem. Find the inverse Fourier transformation of 1 upon 12 plus 7 iota omega minus omega square. Now we solve this problem using convolution theorem to find the inverse Fourier transformation. So first of all, we factorize the denominator here. So this denominator 12 plus 7 iota minus omega square can be written as linear combination of 4 plus iota omega 3 plus iota omega. Therefore, the inverse Fourier transformation of 1 upon 4 plus iota omega 3 plus iota omega equals to Fourier inverse transformation 1 upon 4 plus iota omega times 1 upon 3 plus iota omega. But we know that inverse Fourier transformation of 1 upon 4 plus iota omega equals to square root of 2 pi times e raised power minus 4t u naught t. This can be evaluated by using simple definition of the inverse Fourier transformation. And similarly, the inverse Fourier transformation of 1 upon 3 plus iota omega is equals to square root of 2 pi times e raised power minus 3t u naught t, where u naught t is the unit step function with discontinuity at t equals to 0. Now, if we use the convolution theorem, then we obtain Fourier inverse transformation of this term is equals to the convolution of their inverse Fourier transformations. So this is e raised power minus 4t u naught t convolution, e raised power minus 3 t u naught t. Now, by the definition of the convolution of two functions, it means if we apply this result here, so this implies the integration from minus infinity to plus infinity, e raised power minus 4 of tau h of tau, e raised power minus 3 times t minus tau h of t minus tau d tau. All right. Now, if we simplify, then we get this is equals to e raised power minus 3t times integration from minus infinity to plus infinity, e raised power minus tau, right? H of tau, h of t minus tau d tau. Now, if we simplify this unit step Heaviside function, h of tau, h of t minus tau by using the definition of the Heaviside function, then we get that it is 0 when tau is less than 0 and tau is greater than t. It means this product of Heaviside function has unit value 1 in the interval 0 to t, and outside this interval it has 0 value, right? So therefore, the inverse Fourier transformation of this product is equals to e raised power minus 3t integration from 0 to t e raised power minus tau d of tau. Now, if we simplify this integral, then we get this result e raised power minus 3t 1 minus e raised power minus t for t greater than equals to 0. This is our required inverse Fourier transformation by the application of the convolution of two functions, right? Now, next one is Fourier transform of the Dirac Delta function. So, by the definition of the Dirac Delta function, it is delta of t minus a equals to infinity for t equals to a, and it is 0 for other values of t. Now, and we know the filtering property of the Dirac Delta function, which we have already defined in the Laplace transformation lecture series. So, the filtering property of the Dirac Delta function is given by integration from minus infinity to plus infinity f of t delta of t minus a dt equals to function value at a. Now, if we apply this filtering property, then the Fourier transformation of this Dirac delta function, delta of t minus a is equals to 1 upon root of 2 pi, integration from minus infinity to plus infinity, delta of t minus a e raised power minus iota omega t dt. This is our definition of the Fourier transformation of the Dirac delta function. Now, if we apply this filtering property here, so if we compare, then when we have f of t equals to e to the power minus omega t. So by the application of this filtering property, we have 1 upon root of 2 pi times e raised power minus iota omega a. This is our required solution for the Fourier transformation of the Dirac delta function, right? Next, we define the Fourier transformation of the unit step function. And the unit step function is defined as u of at equals to Heaviside function of t minus a, and it is 1 for t greater than equals to a, and it is 0 for t less than a, right? So therefore, the Fourier transformation of this Heaviside function or unit step function is equals to 1 upon root of 2 pi integration from a to infinity, because it has non-zero value for t greater than equals to a, and it is 1. So therefore, this is 1 times e raised power minus omega t dt. Now, if we simplify this integral, then we get this required result 1 upon root of 2 pi 1 upon iota omega times e raised power minus iota omega a. This is our required Fourier transformation of the unit step function or Heaviside function. Now, let us see the application of the Fourier transformation to solve the initial value problem and boundary value problems. So, in this section, we shall discuss the Fourier transform solution of heat equation, wave equation, and Laplace equation. So, if the Fourier transformation is applied with respect to one of the variables in the given differential equation, then we obtain an ordinary differential equation in terms of the other variable. All right. Now, we solve this obtained differential equation. The solution of the given initial value problem or boundary value problem is then obtained by taking the inverse Fourier transformation. So this is our same procedure as we have used in the Laplace transformation method to solve the initial value problem, right? So let us see the Fourier transform of some derivative functions first of all. So let u is the function of two variable x comma t, be the given function, and suppose capital U function of omega comma t, capital UC function of omega comma t, capital US function of omega comma t, be the Fourier transform, Fourier cosine transform, and Fourier sine transformation of the function of two variable x comma t. So it means these are the suppose the Fourier transform, Fourier cosine transform, and Fourier sine transformation of this function u of x comma t. Then the Fourier transformation of this u of x comma t is defined by u of omega comma t 1 upon root of 2 pi integration from minus infinity to plus infinity u of x comma t e raised power minus iota omega x dx. This is by the definition. It means we are finding the Fourier transformation of this function with respect to x here, right? Now, similarly, the Fourier transformation of the second order partial derivative of u is equals to 1 upon root of 2 pi integration from minus infinity to plus infinity del 2u upon del of x square e raised power minus iota omega x dx. And we know that this is, if we simplify, then we get minus omega square times u of omega comma t as x approaches to plus minus infinity, u approaches to infinity, and del u upon del x approaches to 0. Right. Similarly, the Fourier sine transformation of the second order partial derivative of u is equals to 1 upon square root of 2 upon pi times omega u of 0 comma t minus omega square. This is our Fourier sine transformation of u x comma t, right? Similarly, the Fourier cosine transformation of the second order partial derivative of u is equals to minus root 2 upon pi square root of, and then del u upon del of x at x equals to 0 minus omega square Fourier cosine transformation of u of x comma t. So basically, from these 2, 3, and 4 relation, we can see that Fourier sine transformation is applicable to solve the initial value problem when the given initial condition is of this form u of 0 comma t. When your given initial condition is of this form, derivative form, then we apply the Fourier cosine transformation. Right? So next one is the selection of Fourier sine transformation and Fourier cosine transformation. It means when we have to apply the Fourier sine transformation or Fourier cosine transformation to solve the given initial value problem. Now, if your condition is of this form, it means initial value at x equals to 0 is given of this form u of x comma t x equals to 0 is given. Then we use the Fourier sine transformation because we know in this case third property, that's Fourier sine transformation of this second order partial derivative in terms of u of 0 comma t. And if your initial condition is given in this form, derivative form, del u upon del of x at x equals to 0, then we use Fourier cosine transformation, which can be seen from here. Fourier cosine transformation of the second order partial derivatives is in terms of del u upon del x at x equals to 0. It means when your given initial condition is for x equals to 0 is given in terms of u of 0 comma t, then we apply Fourier sine transformation. And it is given in terms of partial derivative del u upon del x, then we use Fourier cosine transformation. So let us see the application of Fourier transformation to solve the initial value problems or boundary value problems. The temperature distribution u of x comma t in a thin homogeneous infinite bar be modeled by the initial boundary value problems. Del u upon del t equals to c square times del 2u upon del of x square, where x is lie between minus infinity to plus infinity and t is greater than 0. The initial condition is u of x comma 0 equals to function of x, and u of x comma t is finite as x approaches to plus minus infinity. Then we have to find the temperature distribution u of x comma t for t greater than 0. All right. So since the domain of the bar is minus infinity to plus infinity, so we use the Fourier transformation with respect to the variable x. So let the Fourier transformation of this temperature distribution function u of x comma t equals to capital U omega comma t. Now taking the Fourier transform of the differential equation, we obtain the Fourier transformation of the left hand side is equals to c square times Fourier transformation of the right hand side term. Now, by the definition of the Fourier transformation, this implies that integration from minus infinity to plus infinity del u upon del t times e raised power minus iota omega x dx is equals to c square times minus infinity to plus infinity del 2u upon del of x square e raised power minus iota omega x dx, because we are taking Fourier transformation with respect to the variable x. Now, so this can be written as du upon dt, all right, and this is equals to minus c square, because we know that which one Fourier transformation of the second order partial derivative is equals to minus omega square capital U omega comma t. So right, so this is minus c square omega square capital U. Now this is our linear differential equation in the dependent variable capital U, and its solution is given by u equals to k times e raised power minus c square omega square t, where k is a parameter function of omega which is to be determined. Now to find the value of this k, writing the transformation of the initial condition, it means we find the Fourier transformation of this initial condition. Right? We obtain that Fourier transformation of u of x comma 0 is equals to Fourier transformation of the function f, which suppose this is capital F omega. Therefore, u of omega at t equals to 0 equals to k from this one, right? Because if we put here u of, if we put t equals to 0 here, then we find that u of omega comma 0 equals to k, which is equals to f of omega, because your initial condition is given of this form, right? So, and therefore the u of omega comma t equals to f of omega times e raised power minus c square omega square t. So the solution u of x comma t of the boundary value problem is the inverse of this capital U of omega comma t. Therefore, the taking the inverse Fourier transformation of this term, we find that u of x comma t is equals to 1 upon root of 2 pi integration from minus infinity to plus infinity capital U omega comma t e raised power iota omega x dx. This is the inverse Fourier transformation of left hand side, and similarly inverse Fourier transformation of the right hand side. Now, if we simplify the right hand side term, 1 upon root of 2 pi, and we know that capital F omega is the Fourier transformation of small fx. So this one is minus infinity to plus infinity f of xi e raised power minus iota times omega xi d xi, and 1 upon root 2 pi times multiply 1 upon root 2 pi times becomes 1 upon 2 pi, and this is our remaining term. Now again further we simplify, then we find 1 upon 2 pi times integration from minus infinity to plus infinity, integration from minus infinity to plus infinity f of xi e raised power minus iota omega xi minus x e raised power minus c square omega square t d of xi d of omega. Now if we use the Euler's formula here, e to the power iota theta, which is cos of theta plus iota sin theta, then this equation becomes combination of these two terms. This is our real part of the integral, and this is our imaginary part of the integral. All right. Now, since integrand of the imaginary term is an odd function, because as you could see from here, that the sine of omega xi minus x, and this is odd function, because if you put omega equals to minus omega, then it becomes minus times sine of omega. And by the property of the odd function, we find that the value of this integral becomes 0. So therefore, we left out with only the first term here. So therefore, the temperature distribution of the infinite bar is given by u of x comma t equals to 1 upon 2 pi times double integration over the minus infinity to plus infinity f of xi cos of omega times xi minus x e raised power minus c square omega square t d of psi d of omega. This is our required solution of the infinite bar. Alright. Now let us see one more application. The temperature distribution u of x comma t in a thin homogeneous semi-infinite bar can be modeled by the initial boundary value problem. Del u upon del t equals to c square del 2u upon del of x square, and x lies in the semi-infinite region 0 to infinity for t greater than 0, and the initial condition u of x comma 0 equals to fx for x greater than 0, and u of 0 comma t equals to 0 for t greater than 0. Find the unit temperature distribution u of x comma t for t greater than 0 and x lies between 0 to infinity. The domain of the definition is 0 to infinite. It means semi-infinite domain. So hence we use Fourier transformation or Fourier cosine. So we cannot use Fourier transform here because Fourier transformation is applicable over the infinite plane, because limit of integration are from minus infinity to plus infinity. But here domain is 0 to infinity. So therefore we cannot use Fourier transformation. So we have two options here, either Fourier sine transformation or Fourier cosine transformation. As we know that Fourier sine transformation is applicable when your given condition is of this form u of x comma 0 or u of 0 comma t, right? Like, or if your condition is in derivative form, then we use Fourier cosine transformation. So here the initial condition is of this form, so we use Fourier sine transform is here. So let Fourier sine transformation of this temperature distribution function u of x comma t equals to u suffix s omega comma t. Now taking the Fourier sine transformation of this given differential equation, we obtain that Fourier sine transformation of del u upon del t equals to c square times Fourier sine transformation of del 2u upon del of x square. And by the definition of this, we get that derivative of us with respect to t equals to c square times. And we know that the Fourier sine transformation of the second order partial derivative is square root of 2 upon pi omega times u of 0 comma t minus omega square Fourier sine transformation of u x comma t. Right? And now if we simplify by using this condition u at 0 comma t equals to 0, then this term becomes 0. So we left out with only this term. So this is dus upon dt equals to minus c square omega square us omega comma t. So, and this is your linear differential equation, and its solution is given by this one us omega comma t equals to k times e raised power minus c square omega square t, where k is any function of omega. Now to find the value of this k, we use the given boundary condition, and we take the sine transformation of the boundary condition, the Fourier sine transformation of u of x comma 0. This is us omega comma 0 equals to f of x equals to fs omega. Therefore, now we put here t equals to 0 here. Then we get u of s omega comma 0 equals to fs omega, and therefore us omega comma t equals to fs omega e raised power minus c square omega square t. Now to find the solution of the given differential equation, we need to take the inverse sine transformation of u suffix s omega comma t. Therefore, taking the inverse sine transformation of us omega comma t, we obtain that left hand side is u of x comma t equals to square root of 2 upon pi integration from 0 to infinity fs omega e raised power minus c square omega square t sine omega x d omega. And if we simplify this one by the definition of the Fourier sine transformation, we know that this is square root of 2 upon pi integration from 0 to infinity f of xi sine of omega xi d xi. All right. So this is our required temperature distribution of this semi-infinite bar. Right. So thank you for today, and this is all about the Fourier transformation. And in the next lecture series, we continue with Z transformation, and